All right, so today I'm going to tell you guys about software systems for analog hardware, for analog computational paradigms. But before I do that, we're going to talk a little bit about how computation works today, right? So if you think about a computer, you typically think about some sort of on chip that implements digital logic, right? With this computational paradigm, you're going to do computation with digital logical elements. These might come in the form of ALUs, FPUs, and so on. And what these do is they basically update program state, which are stored as digital bits in things like memories, caches, and registers. And so the compiler's role with a computational model is to basically automatically map the target program, and whatever your favorite high-level programming language is, down to low-level instruction-based implementation that the digital computing platform can understand. But today we're not talking about digital computing. We're going to be talking about a different computational paradigm, and that is analog computing. So what is analog computing? Well, it's a computing paradigm where you use the physics of the analog substrate to compute program results. And so in this context, what this means is that the compiler's role is to basically tune the physics of your hardware to implement high-level computation. Now, you might ask, what do I mean when I say an analog computing substrate, right? What can this analog computing substrate be? And the answer is it could really be anything with interesting physical behavior. Here are some examples of different analog computing platforms that researchers have written about. On one hand, you have analog computing platforms that use analog circuits, and on the more extreme end, you have analog computing platforms that use honey and sand or plates of glass. So how is data represented in the analog substrate? Well, it'll depend on the material properties of that substrate. For example, if you're analog circuits, chances are you are representing program values with analog currents and voltages. If you're working with photonics, chances are you're going to be encoding your data in the phase of the photons. And if you're working with something like honey and sand, you're going to encode your problem using the geometry of the material. So we talk about how data is represented. Next question might be, well, how do you do computation? And the answer, again, will be, it depends on the analog substrate. Depending on the materials you are using, there will be different physical behaviors that you leverage to do computation. For example, if you were to use this glass plate-based form of computation, you're going to leverage the diffraction properties of light to implement computation. If you use in-memory computers that leverage resistances to do linear operations, you are going to use Ohm's and Kirchhoff's law to do matrix vector multiplies. The take-home here, though, is that you're going to have a weird set of operators you can work with, and some computations will be easy to implement, and some computations will be very hard to implement. For example, if you consider a photonic computer, you can do a Fourier transform basically for free. But if you want to multiply two values, that is exceedingly difficult. So anyway, a lot of strange primitives that you have to work with when you're working with an analog computational model. The other challenge with doing analog computation is you don't get to pick and choose the analog behaviors that affect your computation. Typically what happens is you work with a material, and there is a superset of analog behaviors that will influence your computation, and you're only leveraging a subset of them to do the actual operators, to implement the actual computational operators. And so what this means is that the analog substrate also has unwanted analog behavior that is not useful to the computation or is even detrimental to the computation. So when you want to map your computation to analog hardware, you must first figure out how to implement the computation with the unusual analog primitives available in the hardware substrate. And you also need to find a way to attenuate away the unwanted analog behaviors present in the medium. So how do you program the analog substrate? Well, there's two different methods. First off, you can basically reconfigure the device by tuning the analog components on the fly. You typically do this, for example, by writing bits to the piece of hardware. And then the more exotic method is you could actually, in some use cases, you actually fabricate a fresh instance of the hardware that implements the desired computation. For example, for this diffractive optical network, you fabricate a separate plate for any operation you want to perform. And the reason why this is reasonable is you can do it with less than $100. So anyway, a lot of different ways to program these systems. Anyway, there's a lot of interesting research problems here, and analog computing substrates have a lot of very unusual properties that make compilation extremely interesting, to me at least. But you might say, okay, this analog computing paradigm is interesting, it's cool that you're having fun with it. Is it useful? And the answer I have here is yes, it can be. So for example, if you consider this use case where you have an analog signal that you need to process before you, so okay, you have an analog signal that you want to compute on. The standard way to work with this analog signal is you basically sample it at an analog to digital interface, and then the digital computation works with the samples that are produced by that analog to digital converter, right? What you can do instead, though, is you can do some pre-processing in the analog domain using analog computing, and then basically you can digitize the results of that analog computation. And so you might say, well, I don't work with analog signals. Well, chances are you actually do. You just don't know. If you ever use memory, you've probably used an analog signal. So data in memory is actually inherently analog. When you store a bit in a memory device, it is actually being retained as an analog material property, such as a resistance or a capacitance. And then what happens when you read from the memory device is basically what happens is the hardware finds a way to measure the material property. And then there's a thresholding operation that happens that determines if you stored a 1 or a 0. The other place where you see a lot of analog signals is in sensors. So anytime you're working with the environment or sensing information from around you, you are actually working with a signal that's inherently analog. And so actually, if you've used a sensor, chances are you've also used something that does analog processing, because a sensor will have the sensing filament that actually measures the signal. And then there's actually analog processing that happens within the sensor to make sure that it is clean enough for you to use in your downstream computation. So anyway, analog signals appear in practice. We just might not be aware of them. So why do analog computation? Well, first off, it's a very low energy computational paradigm, and it also has a lot of downstream effects. So for example, if you're intelligent about how you do analog processing, you can potentially reduce the fidelity of the samples you need to collect and the frequency at which you need to collect those samples at the analog to digital interface. So what this means is that you can reduce the amount of data that you move across that analog to digital interface, which enables for you to use analog to digital converters that take up less power, less area, and operate at lower frequencies. And this is advantageous because if anyone's worked with ADCs, they're extremely resource intensive. So anything that you can do to make them more resource efficient, it's great. And then this in turn also reduces the performance requirements of your digital computation. Because your analog to digital converters are producing less data at a lower rate, you now have more relaxed real-time deadlines, and you could potentially use a lower power or more energy efficient digital processor. Anyway, so that's one situation where analog computing can potentially have an impact, and actually is already used practically today. Another place where analog computing could be useful is it can be used to work with technologies that are new, but have a lot of growing pains that make it hard to implement digital computation with. For example, what we have to the right here is a flexible integrated circuit. This is a kind of new fabrication technology that enables us to produce circuits that can mount on non-planar surfaces. And so, the benefits here are that you can mount it on somebody's body. They're cheap to produce, so you can do bespoke circuits, which is nice if you're doing something that's custom. And they also can be made biodegradable. But because of the way that you fabricate this hardware, you can't miniaturize your transistors very easily. And also, the hardware operates at an extremely low frequency. And so if you were to try to implement a digital processor with this technology, you would end up with something that is not very practically useful. And so with analog computing, because you use fewer devices and you can do meaningful computation at lower frequencies, you can basically get some near-term benefits out of emerging hardware technologies without requiring that fabrication processes improve significantly. Okay, in any case, analog computing can enable more efficient processing of analog signals. It can enable us to reduce data movement overheads when we're working with analog interfaces. And it can also enable us to better use emerging technologies. However, today, it is challenging for someone who isn't an analog expert to incorporate analog computation into their workloads. And so a lot of my research interests kind of revolve around this idea of developing software systems that enable analog computation to be incorporated into workloads more easily. And these might come in the form of design time tools that help domain experts work together with analog designers to develop reconfigurable front ends. Or they can come in the form of compile time and runtime tools that help domain experts more easily use configurable analog computing platforms. And we will actually be talking specifically today about a compile time tool that enables the more efficient use of a reconfigurable analog computing platform. Okay, so at this point, hopefully we understand what analog computation is, and we have an idea of maybe under what conditions it could be useful. So next, maybe it'd be interesting to talk a little bit about, well, what does it take to build a compiler for this for these classic hardware platforms? Namely, because a compiler, again, is an automated procedure that is going to map programs to instructions that the hardware can understand. Basically, another way we can think of this question is, how do we automatically program analog hardware to perform computation? And the best way to do that is with an example. So let's go through the process of building a compiler for this piece of analog hardware. This here is a differential equation solving analog computer. It is not a bunch of vacuum tubes. It is actually a CMOS chip that is made up of transistors. So it's the same kind of device technology that we see in digital circuits. But the difference is the analog behavior of the transistors are being used to do computation. And so it's programmable. So I'm not using patch cords to program it. You can set bits on an SRAM, and that will enable you to program the hardware. And it's an attractive hardware platform for 2 reasons. First off, it's low power. It consumes microjoules of energy and consumes between microwatts to milliwatts of power. And then the second benefit of this hardware platform is that you can actually figure out at compile time how long your computation will take to run, which is very nice for real-time applications. And this is actually not necessary. This is a characteristic of the way we do computation, actually. So anyway, it might not surprise you that this class of analog hardware platforms they're not general purpose computing platforms, right? We're not going to be running Emacs, right, with this hardware. We're going to be doing a very specific subset of computations. We are going to be executing dynamical systems. Now, what is a dynamical system? It is a mathematical primitive we see in many different fields. Relevant fields include controls, signal processing, biology, chemistry, physics, even machine learning nowadays. And basically, it's a mathematical construct that appears everywhere. And a common way that dynamical systems are written are with differential equations. But I'm intentionally keeping it vague because there are dynamical systems that you do not write with differential equations. So anyway, that's what a dynamical system is. What can you do with a dynamical system? Well, one thing you can do is you can use it to study a physical phenomena. And so what you do there is you observe some phenomena in nature, you mathematically model it with a dynamical system, and then you run that dynamical system under a variety of different conditions to gain a deeper understanding of the phenomena. You can also use a dynamical system with a sensor, and you can use that dynamical system to extract higher order information about your surroundings. So for example, you can have a dynamical system work together with an IMU to extract positional information of the object that the IMU is mounted to. Or you could use a dynamical system to monitor a time series signal and identify when an anomaly is occurring. You can, of course, complete the loop, and you can use a dynamical system with a sensor and an actuator, and then you have a control system, right? And there, typically, what you're doing is you're observing the environment, and then you're adjusting sort of actuator elements, such as a heater or something that doses medication, to reach some sort of target goal, right? A classic example of this is a thermostat, right? You set the temperature you want, and it's going to adjust the heating element based on the temperature in the room. You also see this in biomedical applications. Okay, so we understand the application domain. We understand at a very high level the hardware. How do we program and execute computation on this class of analog computers, right? And it might not surprise you that programming this hardware is a little strange. So within each of these devices, there are collections of computational blocks. And as I mentioned before, these hardware platforms are digitally programmable. And there's 2 different ways you program this hardware. First off, you can enable bits within the hardware to enable connections within the chip. And you use this to form circuits, right? And so you can use this programming method to form a variety of different circuits that connect together blocks in the hardware. The second way that you program this hardware is you write bits to each of the blocks. So it turns out these blocks are digitally tunable. And so by configuring the bits in the block, you can kind of adapt the behavior of the block to implement the function that you want, right? So you do that for the blocks that you're interested in using. And then, of course, your goal here is to form a circuit composed of configured blocks where the physics of the circuit, the trajectories of your currents and voltages over time, are analogous to the dynamics of your dynamical system. And so, for example, you might form the following circuit because the physics of the circuit model the dynamics of a car, we'll say. And so the way you execute computation is you power on the device, and then you observe particular signals in your circuit. So for example, you might be interested in the current moving through this wire and the current moving through this wire. And the reason why you're interested in these 2 specific currents is because they correspond to properties of the dynamical system that we're modeling. So you can imagine, for example, the current on this wire corresponding to the velocity of the car that we're modeling. And the current moving through this wire would correspond to the position of the car that we're modeling. And so how do we collect program results? Well, what we do basically is we route the signal of interest to a particular point within the hardware. And then that basically maps to a pin on the device, which we can then route to an oscilloscope. And so you'll see the program results, right, on the scope's display. Similarly, if you want to provide an input into the hardware, like from a sensor, for example, it's actually fairly straightforward the way you do this. You just take the leads from the sensor, and you stick them into a specific set of pins on the hardware. And then what happens is this becomes internally accessible within the hardware. And then you can route it into your circuit, right? And for those of you that are more mathematically minded, you can think of this as a forcing function into your dynamical system. So now you have an open dynamical system. So of course you don't have, and so of course these analog computing platforms naturally work with analog inputs and outputs, but you don't have to provide analog inputs and outputs, and you don't have to provide inputs and outputs in analog. You can, for example, measure digital outputs, provided you first convert the analog signal to a sequence of digital samples. And the way you do this is with an analog to digital converter. Similarly, if you want to provide a digital input into the system, a digital time evolving input into the system, what you would do is you would provide your samples through a digital to analog converter, which will turn that into an analog signal. Okay, so that's how you program the hardware. So you might ask, okay, well, I understand how to program it. Why is it hard to program? So it turns out this class of hardware platforms has some very interesting characteristics that make them a challenging compilation target. First off, there's a very wide variety of programmable analog blocks that the hardware may implement. So there isn't really a universally agreed upon set of analog primitives that are universally implemented by all of the practitioners. And what makes things more challenging is that these analog blocks are designed for both efficiency and usability. And so you might, for example, have a hardware platform that only has that orange block. And this where if you look at the dynamics of this orange block, it implements 2 straight line functions, 1 differential equation, and it has an initial condition. So now you have to figure out how to cobble together these orange blocks and configure them to implement your computation. Conversely, you could end up with a purple block, which implements all sorts of exciting variants of multiplication, none of which are actually classical multiplication. So you have to work with these unintuitive primitives to figure out how to implement your computation. And that's not even the end of it. It's not enough for you to consider the basic functional behavior of the block. And that's because if you remember from earlier, the analog hardware is prone to a lot of physical behaviors, and we're only using a subset of them to do computation. And so in addition to having to consider the basic input-output relation implemented by our block, you also have to consider all of the analog behaviors that might influence your computation. And so what this means is that in addition to considering the function implemented by the block, you have to think about the operating range and frequency limitations imposed by the hardware. You have to think about the effect of analog noise on your computation. If you have any digitally settable values, you have to think about the effect of quantization error on your computation. And because we're using the analog behavior of transistors, and because transistors are subject to process variations, so fabrication variations that are introduced when you make the chip, you also have to think about the effect of fabrication on your computation. So there's a lot of other behaviors that we have to consider in addition to just trying to figure out how to compose together these blocks to implement our computation. Okay, so for my prior work, I developed a set of compilation techniques for this class of devices, and I built the first ever compilation toolchain that targeted a real fabricated device of this class. And so what does compilation look like here? So as a compiler's person, I like to first talk about the inputs and outputs, and then we look at the middle. And so the first input I want to talk about is our dynamical system. And to do that, I'm going to walk through the hello world of dynamical systems, the harmonic oscillator. And so you can think of a harmonic oscillator as a mass attached to a spring, right? And basically, we're interested in modeling 2 properties of this mass in our dynamical system. We want to model the position in meters relative to the resting position of the mass. So this is the resting position. And so if it's a positive p, it would be like displaced downward. And if it's a negative p, it would be displaced upward. And we're also interested in modeling the velocity in meters per second. So we're going to model these 2 properties of the mass. And so we're going to start the mass at a position of 10 meters. So we're going to stretch that mass. We're going to stretch the spring, right, to displace it 10 meters. And the mass is going to start from a standstill. So the velocity will be 0 meters per second. And so if you were to release the mass from this position, you will see that the position evolves as follows, and the velocity evolves as follows. You see it's oscillating, hence harmonic oscillator. So that's the intuition behind the harmonic oscillator. Now we're going to use differential equations to describe the dynamics of a harmonic oscillator. Here are the differential equations, or the dynamical system that describes a harmonic oscillator. As you can see, these are 2 first-order ordinary differential equations. One differential equation describes the behavior of the velocity of the harmonic oscillator. It's right here. And it's a function of position. And then the second differential equation describes the position of the harmonic oscillator, right? So it's going to describe how the position changes over time. And on the right here, we have the initial condition, which is the initial state of the system. So the compiler, of course, works with the specification of the dynamical system. Here's the specification of the harmonic oscillator dynamical system. Should look very familiar. As you can see, there's two equations that describe the velocity and positions dynamics. There's the initial condition over here. And we have this observe P statement, which tells the compiler, hey, make sure that we can measure the position P of our harmonic oscillator. Okay, so that's a dynamical system. That's our program, right? The compiler also works with a specification language that describes the capabilities of the hardware. And the reason why the compiler works with the specification language of the hardware is that we can potentially target other hardware platforms, right? And so this hardware specification language is going to capture two things. It's going to capture connectivity limits, the limitations on the connectivity of the blocks, and it's going to capture the behavior of each of the blocks that are available. And so we're going to talk a little bit about the block specification language. And so each block specification is going to capture the programming interface of the block and the input-output relations implemented by the block. So for example, this is the int block. It has an input x and an output z, and has a digitally settable value z0. It accepts an analog current into x. It's going to integrate that analog current and divide it by 2, and then it's going to produce the integrated signal at z. The initial value of the integrated signal z is determined by the digitally settable parameter z0. This block also has another programming interface, and that is it can be put in one of many different modes. And so this is the behavior of the block when it is in MM mode. If it's in HM mode, it implements a slightly different function. So basically, we have two programming methods. We can basically, you can think of each block as being like parametric. You can configure the kind of the function you want the block to implement by changing the mode, and then you can tune the functionality by setting the parameters and routing signals. The specification also describes all of the analog behaviors I talked about earlier. We're not going to discuss how that is specified. Okay, and the hardware specification language, as I alluded to earlier, also tells you constraints it also defines the constraints that govern how you can connect blocks together. So those are the inputs. Here's the output. So this is a configuration, an analog device configuration. This is the final output of the compiler. And as you can see, it's basically a circuit of configured blocks. So you can basically, what the configuration will do is it'll tell you how to program each block. For example, this call out here states that we should set the digitally settable parameter C to 0.5, and we should put the C block, the CMOL1 block, in the XHM mode. So it's going to basically tell you how to configure the blocks. And it's also going to, the configuration is also going to tell you which subset of digitally settable connections to enable. And that's how you can form the circuit topology. And so that kind of describes the structure of the circuit, the structure of the configured circuit. There are also parts of the configuration that capture the correspondence between your dynamical system and the circuit. So for example, the configuration will also label certain wires with variables. So for example, this configuration labels this wire with P and this wire with V. And that's because the current moving through this wire will correspond to the position of our harmonic oscillator, and the current moving through this wire will correspond to the velocity of our harmonic oscillator. And so it tells you which signals you need to measure to get your dynamics back. The other thing that configuration does is it tells you the correspondence between dynamical system simulation time, hardware time, and wall clock time. So in this circuit, 1 unit of simulation time corresponds to 1 unit of hardware time. And because of the way the hardware is designed, 1 unit of hardware time corresponds to 7.93 microseconds of wall clock time. And so what this means, of course, is the net effect here is that we know at configuration time how long the computation will take to run, right? So for example, if you want to run this circuit for 20 units of simulation time, it'll take 158 microseconds. Okay, so those are the inputs and outputs of the compiler. Next, we'll talk about how compilation actually works. So we're gonna talk about the middle here. How do we get from here to here? Right? So we're going to talk about it first at a high level, and then we're going to do a deep dive. So the first step of compilation is circuit generation. And what this does is it's going to figure out how to cobble together these blocks to implement your dynamical system. So it's going to synthesize a circuit of configured blocks. And so the output of this step of compilation is going to be an analog device configuration, so that configured circuit we talked about earlier. And this configuration is going to have a very specific property. It's going to guarantee that the physics of the circuit match the dynamical system dynamics. At this point, though, we have not yet considered the analog behavior of the blocks. So we are pretending that every block behaves ideally. The second part of compilation changes the circuit to account for unwanted physical behaviors. And so this is the part of the compilation process that is going to deal with noise, quantization error, process variation, and operating range and frequency restrictions. And then the output of the scaling procedure is a scaled analog device configuration which we can then write to the hardware, and we're off to the races. And something I do want to mention here is that this compiler was not designed in isolation. So specifically, that scaling procedure is co-designed with the calibration and characterization algorithms present in the hardware so that we can get a better result. And I'll talk about this a little bit later. So yeah, co-designed. And then I guess the net point here is that by co-designing the software stack with the low-level hardware algorithms, you can basically accomplish more. You can get better fidelity results out of your hardware because there's kind of a cross-stack optimization that's happening. Okay, so now we can look more closely at the individual phases. So let's talk a little bit about circuit synthesis. So you might have remember from before that I said that this analog device configuration is going to produce a circuit, is going to represent a circuit where the physics of the circuit match the dynamics of our dynamical system. And so what does this mean? Well, what this means is I can pick any wire that's labeled, and I can basically begin to walk. So I'll walk through the example here, actually. So let's say we pick this wire here. It's labeled V, right? And what we're going to do is we're going to symbolically walk through each of the blocks to derive the algebraic expressions implemented by each of the other wires. So we walk through the CMOL2 block, and we find that the current being carried on this wire here implements 2 times V. And then if we walk through this integrator block, we'll find that the current carried through this wire implements the following relation. And you'll notice that this wire is labeled P, which means it should implement the position of our harmonic oscillator. And so if we take the differential equation that is implemented by the current moving through this wire, and we compare it to the differential equation that captures the dynamics of the position of our harmonic oscillator, you will see these 2 equations do not pattern match, right? But they are semantically the same. You can basically, with algebraic rewrites, take the top equation and rewrite the system to get the bottom equation. And so you can repeat this for every single labeled wire, and you can confirm that this property holds. This is what I mean by the physics of the circuit match the dynamics of our dynamical system. Okay, so hopefully we understand this notion of matching dynamics. Basically, the circuit generation procedure is going to guarantee that we produce circuits with this property by construction. How does circuit generation work? Well, it's broken up into 3 steps. At a high level, what it's doing is given a dynamical system and the hardware specification, it is going to search over candidate circuits to find a circuit with dynamics that match the input dynamical system. And the search space is extremely large for this part of the compilation process, which is why it is broken up into 3 steps. So basically, we're going to go through each of these 3 steps at a very high level. And so by doing this, you make synthesis more tractable. You can scale to larger problems. It is mostly a performance choice. Okay, so let's talk about the first step of circuit synthesis, and that is sub-circuit synthesis. And what this step of the circuit generation procedure is going to do is it is going to take each of those relations in our dynamical system, each of those equations in our dynamical system, and it's going to synthesize a fragment that implements that equation. And so let's walk through how this works, right? It's going to first pick a relation to synthesize. It's going to pick the position relation. And then it's going to look at the blocks that are available. It's going to non-deterministically pick a block. In this case, it picks the int block. And now the goal becomes we want to get the current at port Z to equal the position P, right? And so we're going to try to get this equation and this equation to be equal, where we have 2 degrees of freedom. We can set X, the input port, to an algebraic expression, and we can set Z0, the digitally settable value, to a constant value. So these are degrees of freedom, and now we have to figure out how to substitute expressions and values into them to get this equation. And so you can see, if you assign X to 2 times V and Z0 to 10, you can get these 2 relations to almost be equivalent, right? Like you can see if you simplify this guy, you'll get this guy, right? But there is one key difference here, and that is the integration here is done with respect to hardware time, and the integration here is done with respect to the dynamical system time. And so to resolve this, all we do is we state to the world, 1 unit of dynamical system time now equals 1 unit of hardware time, and then we're good. And so at this point, the current coming out of port Z now equals P, provided we configure Z0 to 10, and we provide a signal implementing 2 times V into X. And so now, we recursively repeat the procedure. We pick another block, because now we need to implement X equals 2 times V, right? We pick another block, we extend the circuit, we configure the block, and now we get a new expression that we need to implement. But this expression is trivial. So at this point, We basically have a circuit that says if you provide the signal implementing the velocity of our harmonic oscillator into port Q, it's going to produce a signal that implements the position of our harmonic oscillator at port Z. So that's the circuit fragment. So to summarize, we generated a circuit fragment where the physics of the circuit fragment is algebraically equivalent to the position of our harmonic oscillator. And this is a guarantee by construction. So because of the way the compiler works, the dynamics of the circuit fragment will always match the dynamics of the dynamical system relation. And so we repeat the process. Here's the circuit that describes the velocity of the harmonic oscillator. And again, we can confirm, what's going on? There we go, okay. And we can confirm that it's, again, algebraically equivalent, or the dynamics match the velocity of a harmonic oscillator. And then we have this last block, which basically captures the observed P statement. And so the assembly procedure basically routes together signals from where they're used to where they're needed, or where they're produced to where they're needed. For example, V is routed from here to here. With one important caveat, because we're using analog currents to do computation, you cannot use an analog current more than once. Because when you split a signal, because of Kirchhoff's law, you change the signal's values. So you have to also insert copiers. And so the assembly process will figure out where to intelligently insert a copier when necessary. And then at this point, we have a complete circuit. This circuit implements a harmonic oscillator, right? And you can see it has the wires labeled, they implement the position and the velocity, and it has all the blocks that we need to do our computation. Place and route basically maps each of the blocks to the locations in the hardware and figures out how to route signals. We're not talking about that. Okay, so basically, to summarize, the circuit generation procedure generates circuits that implement the desired dynamical system, right? Where, again, the circuit that's generated has physics that match the dynamical system dynamics. So why can't we stop here? Well, let's say we want to run the synthesized circuit on the analog hardware directly. Well, the analog hardware has a lot of physical non-idealities and operating constraints that we must consider. I was not entirely forthcoming, right, with the functionality of this hardware. So it turns out all of these ports can only work with values between -2 and 2. And all of these values, all these programmable values here, have to be between -1 and 1 because of how the digital to analog converters work. And so we basically have operating range constraints that restrict the values that we can work with. We also have frequency constraints. It turns out that if you're using one of these multipliers here, you have to run all of your computations at half speed. And that's because if you start running things faster than that, the multiplier is going to start having all these weird computational artifacts that make the multiplier stop behaving like a multiplier. And so those are kind of hard constraints. There's also soft constraints. All of this hardware is prone to noise. So it turns out no matter what block you're using, depending on the block that you're using, you're going to have, the signal's going to oscillate, or you're going to have this sort of a jitter that is going to be with standard deviation is going to be between 0.01 and 0.04 microamps. And so that's going to be roughly 1 to 4% of your signal's range. And then, of course, there's process variation. And the way the process variation manifests in this hardware is that all of your blocks are going to have coefficients that are not exactly 1. And so, for example, if you have a multiplier block that implements x times y, when you actually look at the hardware, if you use multiplier 1, it might implement 0.97 times x times y. And if you use multiplier 2, it might implement 0.99 times x times y. And if you use a third multiplier, it might be 1.01. So you're going to get variances in how the multipliers behave, honestly, how all the blocks behave. And they're always going to come in the form of these constant coefficients. Okay, so what happens when we run our circuit? Well, consider this. When we decided that we're going to make a circuit where the dynamics of the circuit match the physics, the dynamics of our dynamical system, what we've done is we've directly mapped variables in our computation to analog signals. And so to make things clearer, basically when we labeled this wire P, we said that 1 microamp of current is going to correspond to 1 meter of displacement in the hardware, or 1 meter of displacement in our oscillator. And when we label this wire V, what we've done is we've said 1 microamp of current is going to correspond to 1 meter per second of velocity. And so if you remember from earlier, when we thought about what the harmonic oscillator does when we let it go, the position oscillates between -10 and 10 meters. And the velocity will oscillate between -5 and 5 meters. And so basically, to represent these signals, we need to be able to drive a signal that has a range of at least -5 to 5 on both wires. And if we do propagation of signals, it turns out for every single wire, we need at least a dynamic range of -5 to 5. So basically, we need to at least drive -5 to, we need to be able to represent values between -5 and 5. In some wires, we need to represent values between -10 and 10. This is a problem because every single port requires that the signal fall between -2 and 2. And so what will happen in practice when you run this computation is the signal is going to saturate, and honestly, if the hardware is like not well designed, it could also break the hardware. So not good. And it turns out we're safe because we can't even program this configuration to the hardware because these two values cannot be programmed to the DACs. C here is set to 2 and Z0 is set to 10. We can only write values between -1 and 1. And it turns out before, when we proudly exclaimed that 1 unit of dynamical system time corresponds to 1 unit of hardware time, we've actually also violated that frequency constraint I talked about earlier. Because we have to run things at half speed, which means that we have to map 1 unit of dynamical system time to at least 2 units of hardware time. And another issue that we had when we were mapping the computation is the compiler basically assumed that each of the blocks are going to implement the dynamical, we assume that the circuit will implement the dynamical system dynamics exactly. And we kind of operated under this assumption that each of our blocks are going to deliver the functional specification that was promised. So when we used the multiplier, we assumed it implemented x times y. But based on the discussion we had a few slides ago, we know it doesn't. So basically, we trusted the hardware blocks to implement computation 100% faithfully. They do not. So what's going to happen is the block outputs are going to be different than what we expected, and so our result is going to be off. OK, so to summarize, we produce this analog device configuration where, again, the physics match the dynamical system dynamics. However, in doing so, we did not consider the analog behavior of the blocks. And as a result, we either cannot write our configuration, or we can write it, but it's not going to be able to run, or it's going to run poorly on analog hardware. OK, so what do we do about this? Well, we scale the circuit. And so that's exactly what the automated scaling procedure does. It is going to transform the circuit to account for unwanted physical behaviors. And so this is the part of compilation that reasons about noise, quantization error, operating range and frequency restrictions, and process variation. And then what's going to produce as output is a scaled analog device configuration, which respects the operating range and frequency constraints present in the hardware, and it is also optimized to attenuate away the effects of noise, process variation, and quantization error. So 2 questions. What is a scaled circuit? And if I'm running, and so the scaled circuit, it's running a different differential equation under the hood. And so it's great. It's good that it's running. But I mean, you might ask, well, how do you get your original dynamics back? I wanted to run a harmonic oscillator. If you're running something else, I want to be able to get the trajectories of my position and velocity back from the hardware. So basically, I'm going to talk about what the scaled circuit is and how we recover our original dynamics from the hardware. And so I can't talk about this in a ton of detail, but I will talk about what the scaling transform does. So basically, the automated scaling procedure is going to produce a scaling transform by reasoning about the unscaled circuit. And then the scaling transform can be applied to the unscaled circuit to produce a scaled circuit. This scaled circuit, as I mentioned before, is going to run a different dynamical system. However, we guarantee statically at compile time that the scaled circuit preserves the dynamics in such a way where you can recover your original dynamics by applying an inverting transform that is also produced by the compiler. So let's talk about the scaling transform. You can think about it as a collection of signal scale factors, which is applied to every single wire and port and value in your circuit. And you also have a time scale factor, which captures the correspondence between dynamical system time and hardware time. And so the way you apply your scaling transform is you multiply each digital value with a signal scale factor. And this internally will scale the signals to respect all of the operating range and frequency restrictions and account for the effect of noise and process variation. And then the other effect that applying the scaling transform has is it's going to change the speed of your computation. And that's because it's leveraging a very interesting aspect of first order ordinary differential equations. So basically, the system is going to evolve tau times faster or slower than the directly mapped computation. So if tau is 2, it's going to run 2 times faster, for example. And so once we have our scaled transformation, our scaled circuit, we recover the original dynamics by first measuring the signal. And so this signal, for example, is measured in terms of microseconds of wall clock time and microamps of amplitude. And we recover the original amplitude by dividing the signal by the signal scale factor associated with the port. And that will give us, for example, the position back in meters. And then we divide the time samples by the time scale factor, tau, times the hardware time constant. And that gives us the time in dynamical system time units. OK, so we hopefully understand the scaled analog device configuration. I do not have time to talk about how scaling works. I will tell you that you basically generate a convex optimization problem. The specific formulation is a geometric programming problem formulation. A lot of neat features of that formulation. And then it's going to produce a set of scaling factor and signal scale factor and time scale factor assignments. And there's specifics on this that you can check out in the slide deck. OK, so now we understand how the scaling procedure works. Next, we don't have time for the aside, but I will say that I will make an aside of the aside. So basically, it was very convenient that all of the process variation effects were gains, were constant coefficients on the blocks, because it just so happens convex optimization, this form of convex optimization, is very, very, very good at dealing with coefficients. And this is not actually what happened. There's a trick here. I changed how calibration works to get this behavior. And I don't have time to talk about this, but the point is, instead of us making every single multiplier behave the same, I said, OK, they can all behave differently. I just need to be able to model the differences. And if I have a model of the differences, I feed that into the compiler, and the compiler uses these models to target the hardware properly. OK, so how do the generated circuits perform? As I mentioned before, I targeted a real piece of hardware. This is the HCDC V2 analog computer. I ran 12 benchmarks on it. Here's the reference signals for each of the benchmarks. You might ask, well, what happens if I just don't run the second step of compilation? I just want to run the generated circuit. Well, when you do that, you can't run most of them. And the one you do, you can run. So the green signal here is the scope measurement, so the oscilloscope measurement. And the red signal here is the reference signal. So you can see I only can run one of these guys, and they don't align, right? It's not a very good result. Now, if I allow for automated scaling, but I don't do that co-design that I talked about where I changed how calibration works, I can compile everything. But some of the results, they don't track very closely, right? Now, if I do this co-design step, where I make it so that the process variation behaves in a way that I can compensate for in compilation, then I get signals that very closely track. And so basically, the co-design is an important step to getting this hardware to give you high fidelity results. So basically, with software techniques, we can get better accuracy without actually improving the hardware. So this is the same hardware platform that the guys that fabricated this device used, right? But I got much more accurate results just because I thought carefully about how to optimize the computation to the target hardware platform. And the cool thing here, too, is you can also, when you have software, you can more fully exercise hardware prototypes. And so they were hand coding each of their circuits. And like half of the guy's thesis, literally, was how to program the hardware for like 6 benchmarks. So I was able to scale it to 12 benchmarks, and I was able to generate 200 circuits per benchmark and do kind of distributional analyses of how the hardware behaved. Anyway, so you can do much more thorough studies of how this hardware operates. Anyway, so at this point, hopefully, you understand what it takes to map computation to analog hardware. But you might say, this is all great. I kind of understand the story that you're telling here, but I don't buy analog computing. I still don't think it's something that I should think. I don't see a world where we're going to have to use it. Right? Well, let me paint a picture for you. We are experiencing a sort of renaissance in the hardware community. There's a lot of really neat new device technologies and integration processes that promise to totally revolutionize how we do computation. Some of these technologies, they target new points in the hardware trade-off space. For example, a lot of these photonic platforms promise femtojoule level energy consumption, right? And so, I mean, a lot of these hardware platforms, they promise like low energy consumption, dense data storage, extremely fast computation, and so, in ways that are orders of magnitude better than what we can do today. Some of these technologies also enable the development of new computational elements. For example, people have developed nano devices where you can implement an oscillator with a single device. So if your computation needs oscillating signals, now you can make it with something the size of a transistor, maybe a little bit bigger than a transistor. And maybe if you guys have been following quantum computation, qubits use new emerging technologies, these emerging device technologies. There's ways you can build random number generators that sample from distributions with new device technologies. So you can basically get new computational elements that are traditionally very hard to implement in digital. And also, there's one of the other promises of these new technologies is they promise to ameliorate data movement issues, right? So for example, there's a lot of these 3D like monolithic integration technologies that let you basically densely co-locate memory on top of compute. Anyway, a lot of neat new technologies and integration processes that promise to revolutionize how we do computation. Is there a catch? Yes. Many of these new device technologies are not perfect. It turns out many of these emerging technologies actually exhibit unwanted analog behavior. These non-idealities, these analog behaviors, might disappear as fabrication improves, or they might just end up being a reality of using a particular technology. For example, with resistive RAMs, there's resistance drift. This issue has gotten better as people have fabricated different instances of resistive RAM, but it's still there, and it's a reality if you want to densely store data in RAM. And the other issue here is that we might not be able to initially fabricate emerging technologies at that CMOS transistor size. So we can't hit that 3 nanometer figure with these emerging technologies. Basically, it's challenging for emerging technologies to compete with conventional CMOS, which have had a 75-year head start. So with these new technologies, we cannot escape analog behavior. We're stuck with it, at least in the interim, maybe forever. So basically, in this talk, we talked about this optimistic form of dealing with analog behavior, where we're using some of it to do computation, and we're getting rid of the rest of it. There's also this more pessimistic use case, right, where you have hardware that has undesirable analog behavior that you have to live with, and it has to be eliminated from the computation. And to do that, we need software techniques that can reason about analog behavior when mapping the program to the hardware. Yeah. So in any case, regardless of how analog behavior factors into your computation, into your software stack, I am interested in it. And that's my talk. I'll take questions now.
Oh my gosh, thank you.
Yeah.
I feel like I want to quit my job and learn about this, but that would be completely irrational. I started us a bit late, so this is 200% on me.